Alright, hello everyone. This is a follow-up video to the video I made earlier about how to solve LeetCode 104 maxDepth of a binary tree. But before, I taught you guys how to solve this using a recursion in the form of depth first search. But today we'll be doing breadth first search, which is an iterative approach. So we won't be using any recursion, we'll be using a queue, and we'll have a variable res that's going to keep track of what level we're at. So let me first write that. So res is just going to keep track of the deepest level we found. It's going to start off at 0. And we're going to store the nodes that we're at and the levels in a queue. And it's going to be a 2D queue. So let's say we have the first value will be 3, because as you can see, the first node is 3. And we're going to give it the second value will be the level, so a level of 1. All right. And what we're going to do is we're going to have a while loop that's going to go until the queue is empty. So for the first item, we're going to pop off the first item from the queue, and we're going to get 3 for the node and 1 for the depth. And we'll say, hey, well, our current maximum depth is 0, and we just popped off a 1, so we should make res the max of both of those items. So it will become 1, because the max we found so far. Next, what we want to do is say, hey, does the node we just popped off, 3, I'm going to draw it here because that's where we are at, have a left child? And if it does, we need to append it onto our queue. And it does, so we're going to say queue.append the 9. And for the depth, what we do is add 1 to the previous depth that we had from its parent node, because we know that if 9 is a child of 3, then it is 1 level deeper. So if 3 has a depth of 1, we know that 9 has a depth of 2. So 1 plus 1 is 2, so we'd write 2 here. Perfect. And remember, binary trees can either have 1, 2, or 0 nodes, so we have to at least check the right-hand side. So we say, hey, does 3 have a right-hand child? It does, 20. So we want to append that on. So the node 20. And for the depth, same thing. The parent has a depth of 1, so we want to add 1 to that because it's 1 level deeper, so a depth of 2. Now we continue, and we pop off the 9 because we want to go in order. So now our node is 9, and we have a depth of 2. We see, hey, well, the max depth we have in our global variable is 1, and we just found a 2. So that means we found something deeper, so we no longer care about the 1. So the max depth we found is 2. Right? And we say, hey, does 9 have a left child? It doesn't. The left child is null. Does 9 have a right child? No, it doesn't, so we don't append anything. We'll go through the next loop, and now we're at the 20. We'll pop the 20 off, and we'll say, all right, what is the depth of this node here? It's 2, but our max depth we found is already 2, so we don't have to change it. So now we say, does 20 have a left child? It does, so we want to append 15, or whatever its left child is. So in this case, it's 15. And since the parent had a depth of 2, and we know that this is 1 level deeper than its parent, then we add 1 plus whatever the parent had. The parent had a depth of 2, so that means 15 must have a depth of 3. And we're not done yet. We have to do the same thing to the right-hand side. So does it have a right-hand child? It does. So we append that on, and we're going to do 7 and a depth of 3 because the parent has a depth of 2. And we do the same exact thing, just like before. We pop off the 15, and we're at node 15. So we are currently here. We say, hey, does it have a left child? It doesn't, so we can't append anything. Does it have a right child? No, it doesn't. We can't append anything. We look at the depth. We say, hey, this has a depth of 3. The max we found is 2, so we need to update our global variable to store 3. So the max we found so far is 3. And now we move on to the next node. We say, pop this off. And now we're at node 7. Right here. Does 7 have a left child? No. Does 7 have a right child? No. So nothing can be appended onto our queue. And we check the depth, the depth is 3, but we already have 3 in our global variable, so no need to change. And our queue is empty, and whenever our queue is empty, that means we have traversed every node in the tree. And as you can see, every node has been visited because it's all inside of the queue and with its corresponding levels. And all we have to do now is just return whatever res holds. So in this case, it's 3. We just return 3. All right, so hopefully that makes sense. And if you have any questions, please comment them down below. Now I'm going to get into actually showing you how to code up a solution like this. The first thing I always like to do is zoom in so people can see. And first we have to say, hey, what if they give us a binary tree that's empty? Let's say it has 0 nodes. So if not root, return 0. Because if there's no nodes, then the maximum depth is 0 because there is no depth. Perfect. Next, what we want to do is have our global variable res, which is going to hold the maximum depth we found in our BFS traversal. And here, the next part, what we want to do is create a queue. And we're going to be using collections deque for that. And if you're using Python, all you have to do is say q equals deque, parentheses, and we are going to store our values inside of here. In this case, we want to put the root and the level. The level is 1. Just like when we first started, there was a 3 here and a level 1. In this case, the root will be the 3 and the 1 represents the level. Next, we want to say while q. And while we say while q because this will run until the queue has no more elements. And once it has no more elements, it means we have traversed the entire tree. All right, so we need a for loop. In the for loop, we're going to iterate over the length of the queue. Because as you remember here, if we had only one item in the queue, we need to iterate over all the items. So just the 3. And then when we append the 9 and the 20, we need to loop 2 times to pop off the 9 and the 20. All right, so for, I put blank because we won't be using that variable. So for blank in range length of queue. And this is where we pop off elements. So as you can see, our deque has a root and a level. So we can call the root a node because that's what we're popping off. And the next item is the level equals q.popleft. All right. And if you've never seen pop left before, we're popping left because a queue is first in, first out. And as you can see inside this visualization here, that the items that were added most recently will be in the front of the queue. So we want to get them out as fast as possible. So that's why we need to pop left. And we can't pop normally because that would be the oldest item that would turn into a stack. All right. So now what we want to do is check, hey, have we found a deeper level? So we say res equals the max of res and level. All right, so that makes sure we always pick up the maximum level we found so far. And now we need to append the children. So if node.left, so if there is a node.left, we need to append it onto the queue so we can traverse it. So we need to say q.append node.left, and for the level, you can go level, because it's the level of the parent node, because that's where we're currently at, plus 1, right? And whatever we do to the left side, we have to do to the right side. So I'm going to copy this down, and we're going to change this to a right, and we're going to change this also to a right. So now we check if it has a left node, and if it has a right node. And if it does, we're going to append that onto our queue with the corresponding level. All right. Now, and once this while loop ends and we have traversed the whole entire tree, our res should hold the maximum level we found so far. So all we have to do is say now, return res. And we should submit this and hopefully we get the right answer. And there we go. We solved it and it's pretty efficient. So hopefully you learned something new. And if you have any questions, please comment down below. Peace.